Um, so I want us to look at a follow-up of the topic that I introduced yesterday or in the previous video, that of Brownian motion. So I want to follow it with because in stock pricing we deal with various aspects, because if you want to choose say a derivative for a particular asset, then one has to ensure that there is a match between actually the price, how the pricing of that particular asset and that of the derivative gets in sync at some point. And for that reason, because we have got agreements that traders get into, there is need to have various scenarios up to and including having to consider prices which are maybe referred to as risk neutral, and also at other points, apart from just considering risk neutral, we also want to make the market in such a way that the pricing does not give any advantage does not give any undue advantage to the traders in the market. So we also consider the aspect of arbitrage free. Now, we had looked at Brownian motion yesterday, or the other in my previous video, and we saw that Brownian motion has a part which is deterministic, which we refer to as the drift term, and we also had the diffusion term. The diffusion term, that's the Brownian part, which had the volatility that controls the price of the stock. Today, I want us to consider what we refer to as Martingale. And more specifically, we are interested in its property. And first we note that indeed Brownian motion is a martingale. Yes, we start from there. Brownian motion is a martingale. And what do we mean by a martingale? If I have this part, that is the Brownian motion, being standard, so that like we had said yesterday, if we had a standard, so this should refer to, if WT, let me just say, if WT is a standard Brownian motion, yeah, let me use that short form. If WT is a standard Brownian motion, then expected value of WS given the filtration FT is just this for S greater than T. So we are saying that whenever this particular condition is met, then whenever this particular condition is met, then the martingale property is observed. The martingale property is observed. So filtration here just refers to the amount of information available for that particular, if it is a stock price that we are referring to. So it would mean information that is available up to time t. So, but we are saying that the expected value at time S, the expected value of the standard Brownian motion at time s, given that particular information up to time t, just before s. Because you see, s is greater than t. So in other words, we get to t, then s. Yes, in this case, that's how we are following it. So this is at time s, which is the current, then it's information up to just say maybe previous year or yesterday. So if this filtration then refers to that particular information. But what we are saying is that if it observes a Martingale property, then expected value of this, given this filtration, should just be the current value. Should just be the current value. So it's irrespective of the information available after that particular point. Let's see an example. Let's look at an example. We have that. A gambler bets on coin tosses where if it shows heads, then the gambler scores $1. But if tail shows up, then the gambler loses $1. The gambler loses $1. Yes, the gambler loses $1. So it's a gambling. So that we have two people playing, and the game is we've got a coin which is fair. Fair to mean head and tail are expected to be the weight on the head, the weight for the side containing the head, and the weight on the side containing the tail should be equal, so that whenever you flip it, there is no biasness. It does not have any tendency to have the heavier side landing first. But in this case, we are saying it's equally likely, and that's what allows us to make this experiment. So we have that coin and we are flipping it. Every time we flip it, if it shows a head, I win $1. If it shows a tail, then I lose to my opponent. I lose $1, and then I lose $1. So that being the case, let xt represent the gambler's fortune. Gambler's fortune at time t. That's the gambler's fortune at time t. So we should also see that if that's the case, then if the gambler, when we are starting, we'll be starting at x0, in which case the fortune is 0. If xt represents the gambler's fortune at time t, but then if I set t to 0 when gambling is just beginning, then the fortune is just 0. Nobody has won. So yeah, it is still 0. So x0 is 0. So this represents the fortune. But then we should understand that this fortune will evolve in some pattern. It will evolve in some pattern, like we have. So I will say that xt will evolve as xt minus 1, because if I'm at the current time, then xt has to be some value that we had in the previous play or toss, in the previous toss. Okay, if I'm at the current toss, then my fortune for the current toss would be given that the fortune for the previous toss plus the outcome. Now plus the outcome. So let me just put it, let me give it that symbol. Plus the outcome, where this now represent the outcome of that particular toss. Because what this now means is that at this time, to know my fortune at the current time, I need to add my fortune at where current time here means current toss. So my fortune for the current toss would be given by my fortune in the previous toss plus the outcome in the toss that I'm just about to take, the outcome. But then see that this outcome, so we say, see that this particular outcome can either take, so where we find this, elements in this are contained or are found in this. So it's either minus or plus 1. Yeah, those are the only two options that it can take. Whenever you throw a coin, there are only two options. There are only two chances. Where the first chance is, one of the chances would be you get a tail, in which case you lose, subtracted from you, or you get a head, in which case you win. So that being that, then this is how the fortune will be evolving. So I've used T here to represent the teeth outcome, where teeth, not for it's just the T with this, yeah, will be given by this expression, this particular expression. So let's see. Let's consider then. I hope this is now clear. That's clear. But let me just bring it this end. We may need to refer to it. These are very important results that we need to refer to, where x naught is equal to 0 when we are starting, and xt, that's any toss along for any toss, the outcome, actually the fortune in any toss in the experiment will be given by this particular expression, where I said this represents the outcome of the current toss, and this is the fortune of the previous toss. So that's important. Then let's come here. So what we want to do is to see what we mean by martingales, because I've referred to what a martingale is. Then I want to bring it in line of gamblers, in line of how gambling happens. So let's consider, say, in 4 tosses, for 4 tosses, let's just say 4 tosses. That is first toss, second toss, third toss, fourth. The outcome is given as the outcome for 4 tosses. Consider the following outcomes. Consider the following outcomes. Now, our outcomes are represented by this. So, the first outcome that we have is plus 1. Let me just plus 1 minus 1 plus 1 plus 1. That's the first outcome that we have in photosis. The second scenario that we have is is yes, the second scenario that we have, the outcomes are plus 1, plus 1, minus 1, plus 1, like that. Those are the outcomes. Then the question then is, find x1, x2, x3, x4 in each case, and test if Martingale property is met. If Martingale property is met. That's that. So that's what we want to check. Now we want to look what this, we want to see how then do we check if Martingale property is met or not. And here we are seeing that in photosis, consider the following outcomes. The first case is where in the first throw, the gambler gets a head. In the second throw, the gambler gets a tail. Third throw, the gambler gets a head. Fourth throw, the gambler gets a head. In the second case, first throw, the gambler gets a head. Second, he gets a head. Third, he gets a tail. Fourth, he gets a head. Now we are then asked to find, remember, x1, x2, x3 up to x4 represents the fortune, the gambler's fortune at each particular step. So here, what we want is that in each case, say if it's this, then we need to find the gambler's fortune after the first throw, the gambler's fortune after the third throw, the gambler's fortune in the first throw, the gambler's fortune in the second, the gambler's fortune in the third, the gambler's fortune in the fourth. So once you have had this fortune, in each case, and then you test if these fortunes satisfy the Martingale property or if they meet the Martingale property. Now, this is how we go about this. So first, let's see what will be the fortune, because we had said somewhere that you let xt be the fortune, the gambler's fortune at time t. So if I start with Roman 1, that being my solution, Roman 1, so here I want to see the gambler's fortune here, which will be x1, and I realize that x1 is 1 because that's what the gambler got. It's 1. Then what is x2? What is the fortune of the gambler in the second throw? It's going to be given first. Let's look at this. If I want x2, then I will say it's x1. It's x1 plus the outcome, this epsilon here, the outcome. And that outcome is -1. So it's x1 plus minus 1, which is 1, this, minus 1, and we get a 0. So the fortune in the second throw is x2. And then in the third throw, if then it then means that I'll now bring this, which is 0, plus the outcome in that throw, which is this. So I say plus 1, and I get 1. And for x4 will be, it will be x3, which is 1, plus x3, which is 1, plus the outcome, which is 1. So here I get a 2. I get a 2 as such. So that specifies the gambler's fortune in the first instance. But then we need to check if these fortunes here observe a Martingale property. How do we do this? We would say that if you are to check expected value of x2 given x1 should be x1. So yes, having this side clean, I want us to see what we have. So at time t1, what we have, we want to see, because we are expecting that expected value of x2 given x1 should actually be x2 if the Martingale property is met. Should actually be x2. This value here should be 0 if the Martingale property is met. But let's see. How do we get the expected value? How do we get the expected value of x2? So in the first case, we have that x is 1. That's at time 1. But that is the first throw. So in the subsequent throw, which will be throw 2, x2, actually now this is the fortune in the first throw. So the fortune in the second throw will be given by, there are only 2 possibilities. If in the first this I had 1, then the possibilities are that, the 2 possibilities are that I already had 1, so I can, if I say this, if I take my initial case, which we had as this. So in this case, I say there are only 2 possibilities, that x2, I can either have 1 plus 1, that is if head shows up, in which case my fortune is 2. Or the other possibility is that my fortune can also be in that particular throw, because I'm trying to consider my options before I throw. My option will be 1 and I get a tail, in which case it's a 0. But because each option is equally likely, so I'm going to have it that expected value of x2 is actually half times 2 plus half times 0, which is 1. So we see that expected value of x2 is so this is, there are only 2 chances. It's this half times 2 plus half times 0. But in our case here, we see that we had a tail. Our second case is a tail. The second outcome is a tail. So it means we are going to have this. This is what we settle on. So we see that our expected value when you get a tail, is 0. And that is x2 is 0. So we say that has satisfied the Martingale property. Let me then proceed. I just want to wrap this, but I'll proceed with for x3 so that we see the pattern. Okay. Now, let's check. We see that x3 we are given to be 1. But we want to see if indeed the expected fortune is 1. So our outcome at x2 was 0. That was our outcome. But having the outcome 0, there are only two possibilities: negative, having a tail, or a head. But in our case, we are told we are getting a head. So if we are getting a head, then it means that the expected value of x3 given x2, we are expecting it to be just x2. Yes, so what we have is that in our case, we have the expected, if we have, what we are saying is that for us to observe Martingale property, then this condition has to be met. But then let's see if indeed that is met by by finding the expected value of the fortune at that particular step. So we had that x2 was 0, but there are only two possibilities. You can only have 0, -1 if you get a tail, in which case you have a -1, or you have 0 plus 1, which is 1, if you get a head. And what then would be the expected value of the fortune in that step? It would be half times -1 plus half times 1. That is 0. So we see that indeed it actually observes the Martingale property, because the expected value of x3 is 0, which is consistent with the fact that the expected value of x3 up to the point when we just observed the expected value of the fortune in the second throw is just given by the fortune at the second throw. So that's that. Let me consider the third part. Let me now consider the third part, where now I'll be considering just how to observe them. So now I'll be talking about expected value of x4 given x3. It should just be x3. That's what I want if it observes the Martingale property. But then what is expected value of x4? What is the expected value of x4? What was our outcome in x3? Our outcome in x3 was 1. Our outcome in x3 was 1. Our outcome in x3 was 1. But yeah, our outcome in x3 was 1. So let's see what, because that was x3, x2, now x4, x3, right? So I will have two possibilities. One where I say 1 plus 1, in which case I get 2, or where I say 1 minus 1, in which case I get 0. And that will give me, because they are equally likely, I've got a half times 2 plus a half times 0. And that gives me 1. And we see that indeed, that is the value that we get here. Yes, that's what we have here. So that step again meets the Martingale property. So we would say that this has passed the test. So let's check if the second one And for the values, find x1 fortune at first throw, second throw, third throw, fourth throw. They are these ones. We are actually, they're these ones. They're just these ones. These are the fortunes. These are the fortunes. Yeah. After the first throw, second throw, third throw, fourth throw. So let's check. Let's observe what happens with the second one, if we have it. So the second case, let me rub here. Second case, let me rub this. And so I have x1, fortune x1 is 1. x2 will be 1 plus 1, which is 2. x3 will be 2 minus 1, which is 1. And then x4 will be 1 plus 1, which is 2. So these are the fortunes. That is how the fortune will evolve in the second case, for the second fourth process. But then the second thing, what then we need to check again is to observe if that as well meets the Martingale property. So let's see if it meets the Martingale property, then we'll clearly see. So first, let's see. We are saying that for Martingale, expected value of x2 given x1 should actually just be x1. But what is x1? x1 we are given to be 1. But then what is the expected value of x2? There are only two options. The first option would be where we have, if we have 1, then it's 1 plus 1, you have 2. Or 1 minus 1, and you have 0. So that means the two options are half times 2 plus half times 0. And this gives me 1. So we were expecting, actually what we're expecting is that expected value of x2 given x1 is just x1, which is 1. But in this case, we were expecting expected value of x2 given x1 should just be x1. So we see that actually that is the case, but the outcome is giving us 2. So Martingale property is not observed. The outcome is giving us 3. What we were expecting is that expected value of x2 given x1 is x1. Yes, where x1 is 1. Of course, by calculation, we see that that should be the case. But the outcome that we get is different. So then that already tells us Martingale property is already not observed in the second case. But then we can go ahead and try in the next step. So next step, we would consider for the next step, expected value of x3 given x2. We expect it to be just x2. Yeah, we expect it to be just this. To give us the expected value of x3 given x2 should just be x2. Let's see. But then what is the x2 we are given here already to be 2. 2. And then it then means that expected value of x3 can only occur in 2 circumstances. The first case is where we have 2 minus 1, if it's a tail, in which case you have a 1, or 2 plus 1, in which case you have a 3. So that's going to give us expected value of x3 to be half times 1 plus half times 3. And this This is half. This is actually half plus 3 over 2. That is 2. We get 2. We get 2. So in this case, we get the expected value of x3 to be 2, which is consistent with what we would have expected. But if we check the outcome, it is 1. So again, that is another proof that the second outcome, this, does not meet does not satisfy the Martingale property. So this does not satisfy the Martingale property, but the first does. And that's how you are expected to go through that. So that's about martingales. And this topic, martingales, we have covered it in depth in our course for the actuarial science students, and also for the certified certified finance analyst exams. So if you are interested to know more, kindly contact me through the contact that I've given through my YouTube, on my YouTube page, or you can visit our online school, that is www.mefschool.com. All that information should be available. So if you want to know more, then link up with me. Meet you in my next video.